And my name's Mark. I'm your president, and we'll open with the land acknowledgement. So, as we usually do, we acknowledge our Indigenous family. The lands from which our members and guests are joining us are located on the original lands of the Anishinaabe, Cree, Oji-Cree, Dakota, and Dene peoples, and on the homeland of the Métis Nation. We respect the treaties that were made in these territories. We acknowledge the harms and mistakes of the past, and we dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. Okay, and to open up our meeting, we're at 7 o'clock for the beginner session. I'm going to welcome Gail Wise forward. Thanks, Gail.
Aquila the eagle is south of Cygnus the swan and west of Delphinus the dolphin. The eagle is shown flying towards the east and across the Milky Way. The golden eagle holds a valued place in Native American culture. It symbolizes strength, freedom, and spiritual significance. Among various people, the eagle is often seen as a messenger to the Creator, a symbol of the connection between the earth and the heavens. In Navajo mythology, the golden eagle plays a pivotal role in their rich storytelling tradition, which encompasses profound lessons about life, nature, and identity. The legend of the golden eagle begins with the creation of the world. In Navajo belief, the first man and the first woman created the earth and all living beings. As they populated the land, they called upon the golden eagle to oversee the balance of nature and protect the harmony of their world. Some Native American cultures identify the eagle with the thunderbird. The thunderbird was a mythical super eagle responsible for creating thunder and lightning by beating his wings. He was pretty active this morning over my house. Some believe that the thunderbird's feathers carry prayers to the sun. Eagle totems appear to inspire us to reach higher and to become more than we think we are capable of. The thunderbird symbol is at the top of traditional totem poles in British Columbia, the Pacific Northwest coast of Alaska, and in Oregon and Washington. In the sacred circles of wisdom among these Northwest coastal people, the thunderbird is said to be perched regally atop totem poles to symbolize the ultimate status of an emblem of power. The thunderbird is said to be the supreme chief among the native pantheon of natural spirit energies. Totem poles are traditionally made from the cedar tree, which is considered sacred to the thunderbird. For the tribes of the Northwest, legend states the thunderbird dwells in regal solitude in mystic cedar forests where no human is allowed. In the mythology of other Indigenous people, the eagle plays a leadership role, either as king of the birds or as a chief with whom humans interact. In other legends, the eagle serves as a messenger between humans and the Creator. The golden eagle is also known as the war eagle. It's associated with warriors and courage in battle, and it is golden eagle feathers that were earned by Plains people men as war honors and worn in their feather headdresses. The Choctaw considered the bald eagle, who has direct contact with the upper world of the sun, as a symbol of peace. The eagle plays an important role in the sun dance of the Plains people, and it symbolizes the sun in the rites of some of the southwestern tribes. The Iroquois tell of Keneu, the golden eagle, and of Oshadagia. I even practiced that. There it is. How would you say it? Oshadagia? It's a giant eagle with a lake of dew on his back who lives in the western sky. The Pawnee believed eagles to be a symbol of fertility because they build large nests high off the ground and courageously protect their young. They honored the eagle with songs, chants, and dances. The Comanche's myth of eagle creation began when the young son of a chief died and he was turned into the first eagle as an answer to his father's prayers. The Comanche eagle dance celebrates this legend. The Pueblo people associated the eagle with the energies of the sun, both physical and spiritual, as well as symbols of greater sight and perception. The Zunis carved stone eagle images for protection, crediting to them both healing and hunting powers, and the eagle dance is one of the most important traditional dances held by the Hopi and other Pueblo people. The Navajo people have a myth that says eagles originated when a warrior, Nayanezgani. Now, I practiced that too. There it is. How would you say that? Nayanezgani. Please forgive me. I know I'm saying it wrong. He slayed a monster who lived at Wing Rock. Afterwards, he turned into the eagle's offspring, who were now alone in their nest. Rather than have them grow up evil, he turned the youngest into an owl and the oldest into an eagle, who would be a source of feathers for rites and bones for whistles. Among the ancient Aztecs, legend says that during the creation of the world, the eagle and the jaguar fought over who would have the honor of becoming the sun. They say the eagle settled the matter by flying into a fire and becoming the sun. The jaguar followed close behind, and he settled for becoming the moon, with the spots on his coat showing that he had only been partially burned. The Aztecs also believed that their chief god told people to settle at a place where they found an eagle perched on a cactus and eating a snake. Legend says that place is Mexico City. To the ancient Greeks, an eagle has always been a bird of kings. Aquila could fly the highest of all, and he performed many difficult tasks for Zeus. Aquila was at Zeus's side during the Battle of the Titans, which was a fierce war among the gods to see who was the most important in the universe. Now, of course, we all know that cats are most important in the universe, but the Greeks had some pretty good stories anyway. On one occasion, Zeus's daughter, who was the cupbearer to the gods, and who had the power to restore youth and beauty to gods and men, twisted her ankle, and so she could not be hostess at the table of the gods. Zeus ordered Aquila to fly down to earth and select the most handsome youth he could find to serve as wine pourer at the banquet. Aquila sailed down from Olympus and noticed Ganymede, who was peacefully tending his father's herds. The eagle hovered overhead, and then with great skill, he dived down, lifted Ganymede in his talons, and flew back to Olympus. So Ganymede was promoted from a shepherd to be a celestial waiter of the gods of Olympus, and he pleased the eye of all with his manly beauty. Ganymede was then immortalized as the constellation Aquarius, which is just south of Aquila. In honor of his faithful service, Aquila was immortalized by being placed in the stars. The name Aquila means eagle, and it was given to this constellation when it was near the summer solstice. The bird of highest flight was chosen to represent the greatest elongation of the sun. The four constellations, Aquila, Aquarius, Capricornus, and Delphinus, are all relatively close together in the sky, in a region that's almost empty of deep sky objects. Aquarius and Capricornus are away from the main body of the Milky Way, and they only have a few faint galaxies and star clusters. But Aquila and Delphinus are right along the Milky Way, and they have some very nice examples of planetary nebula and dark nebula. Even though there are only 4 Messier objects in this whole area, there are still enough deep sky objects to keep an astronomer busy on a summer night. The stars in Aquila are mostly 3rd and 4th magnitude, except for Altair, the eye of the eagle, which is magnitude 0.82. This is one of the stars in the summer triangle. The other 2 are Deneb in Cygnus the Swan and Vega in Lyra the Lyre. So you can find Aquila even before it gets really dark. The name Altair is from the Arabic for the flying one. It spins very rapidly. It makes 1 revolution in only 6.5 hours. This rapid motion deforms the star so that its equatorial diameter is twice its polar diameter. Altair is 1.5 times bigger than our sun, and it's 11 times brighter. It's only 16 light years away from us, which is very close in the world of stars. The second brightest star in our Eagle is Beta Aquila. It's called Alchéan for the Falcon. Its magnitude is 2.86. And Gamma is Tarazed, the plundering falcon. Its magnitude is 3.86. Eta Aquila is a variable star. Its magnitude ranges from 4.1 to 5.3 every 7 days, so you can see its changes of brightness visible to the naked eye. As I mentioned, there are a lot of planetary nebula in Aquila. NGC 6781 is one of the largest and brightest planetaries in the whole sky. It's known as the Snowball Nebula. This is against a really rich background of Milky Way stars. It's extremely easy to find, right on the line between Zeta and Delta. Zeta is that top star in the wing, and Delta is the middle star there. It's just 3.8 degrees north-northwest of Delta. Its magnitude is 11.4, and it's really huge. It's 106 arc seconds in diameter, which is nearly 2 arc minutes. So it's a little bit bigger than the size of the Owl Nebula, M97 in Ursa Major. Now this one looks a lot better with an O3 filter. That will really bring it out. Its central star is magnitude 16.7, and the main body of the nebula is like intersecting rings, sort of like a mini helix nebula, or my personal favorite, the Cat's Eye Nebula. There is a lot of interstellar dust in this area, and within a few degrees, there are a lot more planetaries. NGC 6772 is magnitude 14, and its size is 84 arc seconds, which is 1.4 arc minutes, so it's very big. It's estimated to be about 11,000 years old, which makes it one of the oldest planetaries. NGC 6778 is magnitude 14.5, but this one is really teensy. It's only 12 arc seconds in diameter. It was discovered by a German astronomer named Albert Marth sometime in the period of 1863 to 1865. And then English astronomer John Herschel may have mistakenly catalogued it as NGC 6785 because now nothing can be found at the coordinates that he gave for that one. In the new general catalog, it is described as a small, elongated, ill-defined disk, and I see the shape of the Dumbbell Nebula here. NGC 6804 is magnitude 13.4, and it measures 0.58 arc minutes across. Stellarium calls this one the Incredible Shrinking Nebula, but I could not find any information why. I was really hoping I could because it sounded like there might be an interesting story there. Right next to this one is NGC 6803. Its magnitude is only 15, and it's really small. It's only 6 arc seconds in diameter. Even though these two are very close together in the sky, they're not physically related. Now for my favorites, the open clusters. NGC 6709 is a loose open cluster that's located in a very rich section of the Milky Way. The cluster is fairly rich. It has about 40 stars that are Nernst magnitude and fainter, and its total magnitude is 6.7, so it's quite bright. Stellarium calls this one the Flying Unicorn Cluster, and it measures 8.7 by 8.7 arc minutes, so you'll need at least an 8-inch telescope to appreciate this one. It's very near the center of our galaxy, and it's only 5 degrees south of Zeta, which is the top star there. NGC 6755 and NGC 6756 are in the same field, only 30 arc minutes apart. 30 arc minutes is the size of the full moon, so you could get the full moon in between those two. That's how close together they are. NGC 6755 is 10 arc minutes in diameter, and its total magnitude is 9. It was discovered by William Herschel on July 30th, 1785. And it forms a double cluster, the NGC 6756, which is only 30 arc minutes away. This one is much smaller. It's only 3 arc minutes in diameter, and its magnitude is 10.7. It's much more dense than NGC 6755, and it's a bit difficult to find. You will need a star chart. It looks very much like a globular cluster, except that you can see the individual stars. Across the Milky Way from Altair, we can see an even brighter star, Vega, or Vega, or Vega, or Vega, however you want to say it. That's fine. I still say Vega. That is in the constellation Lyra the Lyre. Vega is a weaving princess, and Altair is her cowherd lover. Vega is the daughter of the Sun King. She is very clever and skilled at weaving, and she could make the most beautiful tapestries. One sunny summer day, she happened to look out of the palace window, and she saw her father's herdsman driving the king's cattle along the banks of the Milky Way. As often happens in these stories, their glances met, and they both knew that it was love. The king had been worried about his daughter's future, so he was delighted when he heard about their romance, especially as Altair was a very conscientious worker who always looked after the cattle with the greatest care. The princess wove her own wedding dress out of the sparkling rays of starlight, and the two were married. They were very happy together. In fact, they were a little too happy and a little too devoted to each other. After a while, they forgot all about their work. The weaving loom stood still and gathered dusty cobwebs. The royal cattle roamed far and wide across the heavenly meadows. The Sun King kept warning them, and every time they promised to mend their ways, but soon they lapsed into idleness again. This annoyed the king so much that after several warnings, he decided to banish the husband to the other side of the Milky Way so that he could tend the cattle there. After Altair had gone across the one and only bridge, the king had both sides closed by barriers, and a guard was posted with instructions that neither of the couple would be allowed to cross. The princess pleaded with her father, but he would not listen. Finally, she appealed to a flock of magpies who had pity on the couple. The magpies decided that once a year, on the 7th day of the 7th month, they would help the lovers. On that day, all of the magpies would fly to the Milky Way and make a bridge across it. The young couple would rush into each other's arms and spend the rest of the day together. On that day, a soft rain began to fall, which was their tears of happiness. But at night, the soft rain became a downpour caused by their tears of having to part again for another year. Sometimes these stories have a happy ending, but sadly, this one does not. Just to the southwest of Aquila is the little constellation Scutum the Shield. This is not an ancient constellation. It was invented in the year 1684, and its stars form sort of a squashed diamond shape. I really like this constellation because it has my very favorite Messier object, M11. In fact, it's my very favorite object in the whole sky. And I actually use the stars of Aquila to find this one. It just follows the curve of his tail. M11 is also known as the wild duck cluster. This is one that I keep going back to. At Glenlee, it is beautiful, but under a dark sky, it is really spectacular. All these little bitty white stars against a really dark background, you have just got to see this one. It makes me think of that superfine sugar that I use when I make Christmas cookies. Apparently it's called the wild duck cluster because it looks like ducks in flight, but I don't see that. I just see my Christmas sugar. The cluster's magnitude is 5.8 and it's 9 by 9 arc minutes, so you can easily pick it up with your binoculars. But use a telescope, and I hope you'll like this one as much as I do. Scutum also has another Messier object, open cluster M26. This one is magnitude 8.87, and it measures 6 by 6 arc minutes. This one will be a little bit of a challenge to find with your binoculars, but a small telescope will show it nicely. You don't have to be eagle-eyed to find Aquila the Eagle. Just remember that his brightest star is part of the summer triangle, and he will be there to guide you all through the night. The end.
Excellent, thank you, Dale. Okay, we'll get into our announcements this week. As many of you probably know, we had the loss of a dear member, a former member, and a former president of our club, July 26th, Peter Toth. Peter passed away in his hobby, an experimental aircraft. And for those of you who are interested in memorializing him or attending a funeral, there will be a funeral. I believe it's on the 15th of August, 2 p.m. at Glen Lawn Chapel on Lagimodier. For those of us who remember Peter, he's waving goodbye to us here. He was a cherished member, active former president, and a lovely guy. And actually, I didn't realize until I read this, I share a birthday with him. Same day. Anyway, if we could just have a moment of silence for Peter, I'd appreciate it. Thank you. Okay, we have another significant event for the center coming up this month, of course, the Spruce Woods Star Party, which will be again at the Spruce Woods Provincial Park. We have the group use area reserved for the club. And for those of you planning to attend, there's an Eventbrite link for you to follow. It's $40 for individuals. And I think those 12 and under are free, accompanied by a paid adult. Please, if you can, please think about registering as soon as you can. It is refundable right up until I think a week before, if I recall. So it doesn't hurt to register for the event now. And then we have a good handle on preparations and numbers. So anyway, that's coming up. It's a significant event for the center. Please think about registering if you're planning to go. Also in our announcements, I want to take note of a few of our volunteers in the center who look after various events for us and tasks. One of them is Explore the Universe, and I see Stan here today. Oh, excuse me. And Stan looks after our Explore the Universe program. So if you're interested in starting up on Explore the Universe, please reach out to Stan. We also have Mike. I think I saw him come. Yeah, Mike's here for the loaner program. Quite a busy program for us. I think most of the scopes are out, so you might have to line up. I think the Sea Star is especially in demand. So I think that's a really good program for members. And if you're interested in seeing what we have, chat with Mike at the break. Actually, it's a good time. Working along stands on another program here, workshops and ideas. If you have any ideas for workshops, which we host as a center, Stan is he's on that one as well. And then Wing in the back, last row, is doing our Telescopes for Kids program. It's a program that started by Gord a few years back, and Gord's here with us. So we've tried to continue with that program, and Wing is running with the donations, and hopefully we'll have something to hand out to the children this year. Coming up on Friday the 15th, we have a program we've been running for the last 2 or 3 years now with daycare on Carpathia School on Grant Avenue, where we do an astronomy outreach program for children between about 3 and 9. And I'll have to say it's quite surprising with kids that age. One of them, and I mentioned to Adam that last year one of them stumped me, a 7-year-old boy, when he asked me to explain the theory behind a white hole. And I said, a black hole? He goes, no, a white hole. And he was correct. And he actually listed off the Einstein theory behind the concept of a white hole at 7. So don't underestimate these kids. That was one lesson I took from that year. Moving along, Judy, if you have a few moment to talk to us about the Lockhart lecture.
Okay, some of you have been members of the club for a while will remember that there used to be an annual Lockhart Memorial Lecture that the Department of Physics and Astronomy at the university coordinated, and RASC usually participated in this. Dr. Tyrone Woods, who's been one of our speakers in the last year or so, wanted to reactivate it because now there's a bunch of new graduate students and new faculty at the university. And quite a bit of interest. I've been on sort of a working group trying to coordinate what we can do and what we can't do and that kind of thing. I wasn't able to get the public lecture coordinated with a RASC meeting so that it would be one trip to the university, but there is a public lecture slated for the evening of September the 4th on campus. And they haven't yet booked the room, but they have 2 or 3 options, and they haven't yet got a title for the speaker. But the person who's speaking is a theoretical astrophysicist from North Carolina State Department of Physics, and she explores a large range of questions in cosmology, which is the study of the universe from the beginning to the end. And we're somewhere, I don't know if we're in the middle or early or late, or I don't know if it does end, but anyway. She's going to be talking on September the 4th. She's published a lot of popular publications and articles in Scientific American, a magazine called Slate, Sky and Telescope, Time, and Cosmos. And she's a columnist in Cosmos magazine. And the table of contents of a recent book of hers called The End of Everything are kind of a cursory outline of things that she will talk about. She will introduce the cosmos and the Big Bang, from the Big Bang to now and what we can see, talking about something called the Big Crunch, heat death, the Big Rip, vacuum decay, bounce, and the future of the future. Pretty catchy titles for tables of contents, and she's a really dynamic speaker. Anyway, the book is very popular. There's going to be extra copies at McNally Robinson and at the U of M bookstore, so you could bring them, if you buy one, to the public lecture and she would sign it. I wanted to sort of publicize the lecture because I think a number of us will be interested in the cosmology angle and also in seeing a really dynamic speaker in person. Often we have really dynamic speakers in person, but also in Zoom presentations, and it's really great to see them in person. So that's my announcement. Thanks, Mark.
That's an excellent opportunity for us as, as the center members to be able to attend that lecture. So thank you very much, Judy, for pointing that out to us and giving us that heads up. And I think it's a book I'm going to pick up. Now, I guess we have today's Friday, tomorrow night. We have members observing night, and one of our members is hosting the night at Glen Lee, weather permitting. I think it's even, if it's cloudy, there's the warm room, and he will be hosting something indoors as well. So I think we'd have to have a really significant event to have it not go on. So James Fast is hosting the binocular observation. And if you know James, he has quite an impressive collection of binoculars. So it will be an impressive opportunity for you guys to explore the cosmos with James using binoculars. So, I don't think any of the binoculars James has can be handheld. They're excellent. I think one or more of them have the same diameter as one of my better telescopes. And that's two of them together. So that's a real opportunity for everybody. Moving along, sorry, we'll get past Peter. Just a few things. I think we put this up every center just to remind everyone about how to get in touch with members and how to, yes, Wayne, sorry.
Mentioned the Spruce Woods public event on August 30th.
Okay, that's right. We do have an August 30th public event that we do in cooperation with Spruce Woods. August 30th is kind of a trade-off for allowing us to use the park for our Star Party. And I think we have a few folks already set up to look out to attend. Yes, Jay? A dozen? Okay, that's excellent. But we can always use more because the event can oftentimes attract a lot of campers and a lot of folks. So if you can actually make your way out there or you have an opportunity to attend on August 30th, that would be a real benefit to the center and help us maintain that valued relationship with the Spruce Woods Provincial Park. So, and any other announcements from, yes, Stan?
Two things. One, I have keys for the observatory.
Okay.
So if anybody who's a member of the club but does not have an up-to-date key, you can see me. There's a form that you fill.
Excellent.
And the second thing is the club is going to be ordering calendars. I don't know, was the price decided by council?
We haven't actually heard what the final price is, but around $15 is break even.
$15. Yeah, I think the payment means now is to go online.
Yeah.
And to you could pay either by e-transfer or I guess PayPal credit card sort of deal.
Yeah. Yeah, it just has to get to our bank account. So I think I don't think we have an Eventbrite or anything set up for it specifically, but e-transfer for sure works. Trying to use a credit card, I'm not sure yet if we have that set up properly. If you use PayPal, it may work. I don't know for sure though. But the old standby of cash and check still function for us. So, but that does involve handling, and it's a lot simpler for everybody and the volunteers involved if you can e-transfer. So, and if there's anybody needs to know, I can provide or James, the treasurer, can provide the email address. It's the one we've also used for Spruce Woods. Although this year the Eventbrite has the.
So we're in the process of trying to decide how many
to order.
Last year we ordered 25, ordered another 5. There's still people asking. So if you're going to want more than one, well, please contact me. Let me know if you think you're going to be ordering them, and then we'll get an idea. I'll take a list of names of people who want to order calendars, and then we'll hopefully we'll have them. I think in a couple of weeks.
Well, they at least take the order and then they come usually in October, November timeframe.
Yeah.
Usually before the Christmas time or the holiday break. But typically it gets pretty close when they finally get to the printers. Because that's often our astrophotographers across the whole center, across Canada. Or all the RASC, they compete to put their pictures in that calendar. So last year we were fortunate to have a couple of members, or at least one member with a picture in there, so an image.
You go to national and order one.
Yeah.
The price turned out to be about, with shipping turned out to be double.
Yeah, almost double what we would charge. Yeah.
So for the bargaining unit for getting the calendars.
Yes, definitely. Yeah, so don't forget to get back to Stan. I think we have a very short window to order at the discounted price before they go to publishing. So I think before the end of the month, we need to know. Or August the 15th, I think, maybe August the 15th. So if you know for sure, just send a quick note to Stan. Yeah, cash will always work. But even if you just provide them a number, like how many you want, we can pay it, Stan will make sure he collects. Any other announcements? I think that's it. So with that, I think we'll move on to Jay and what's up this month, or actually what's new this month. What's up and what's new? April.
Who'd have thought you could just go and type in, show me a picture of Kermit with a telescope to an AI program, and it looks pretty good. The last time I tried this. Show me a picture of a fox looking through a telescope. He was looking through the wrong end of it. But good luck trying to get AI to have Kermit looking into the telescope because he will be on the other side. So okay, we're back to some darkness in the sky right now, and you can see from this graph and the outlined red boxes where we are from now until a month from now. And we've just started, the black stuff is where it's actually dark enough, where we call astronomical darkness. It doesn't say anything about cloud cover, but you can see that we start with, right in the left-hand side of that box, with a fair number of hours, about 4 of them. So we're into it, and by the time we're finished, we're up to about 6 or a little more hours. So it's time where we can do some astrophotography and where we can have some really dark skies to be able to see some of the stuff that's up in the sky. And there's lots of goodies in August. So we take a look at the sky. I have 2 pictures here of the Milky Way, and one is for August 11 at 10 p.m. The other one is September 11, 10 p.m. month from now. And you can see right now, the Milky Way is very prominent, and especially on the lower end of the picture, the brightest part of the Milky Way, where all the goodies are. And that's where Gail was talking. You can see, well, over on this side, you can see Aquila here. And up in the middle, you see where it says Sig, that star above that is one of the stars of the summer triangle. So you can find Vega there off to the right. So those 3 stars of the summer triangle surround the Milky Way up above. So the center of the galaxy is down low here in, unfortunately, the menu is hiding the pointer that I can turn on. But anyway, the center of the Milky Way is here, where it's all bulged out. There's lots of goodies there, but we're a little bit far north to get the best view of it. So we sort of cruise up in here. Nevertheless, there's some very nice nebula in there, the Lagoon, the Trifid, and so on and so forth. But farther north, we've got some lovely stuff up in when you get up into the Swan here, or Cygnus. A month from now, things have moved along. The Milky Way is now into the southwest part of the sky instead of in the southern part of the sky. It's starting to set a little bit earlier. You can see it's not as high up in the sky over here at the same time. But on the other hand, we still have a really good view of everything up through this part of the Milky Way. And that's where you find most of the nice observing in August, when the evenings are warm. And even into September, a little bit more of dew likely in the middle of the night in September. And it's actually one of the favorite times of years to be doing nighttime observing. And of course, the star party occurs right in the middle of both of these. So all we need is clear skies and an absence of forest fires. Just taking a little bit of a closer look in what's in the southern part of the Milky Way. We have pieces of Scorpius in here. We have little bits of Sagittarius in here. Most of the center of the constellations off to the side. Each one of these little bright spots here represent nebula or star clusters, especially here in Scutum, where the Milky Way is especially dense with stars. But at the same time, with the sea stars and the other automatic telescopes that are available these days, you can photograph the dust lanes up through the Milky Way. Of course, they're easily visible through the eye as well. So this is sort of the view at 10:30 tonight and about 9:30 on September the 11th, a month from now. And when you look at the planets, I have some pictures of these in a minute, but you can see that when we look into August here, that Mercury is really not visible at the start of August, but later on it moves out from behind the sun, and it actually gets its farthest distance away from the sun on the 19th, but it's a morning object, so you have to be up early to see that. But it's worth getting up early because both Jupiter and Venus are very bright, very close to each other in the morning sky. So you could kind of use them as a bit of a pointer toward Mercury, but you'll see later, Mercury is quite a bit closer to the horizon than those two are. Mars is now getting essentially unobservable. You can see it. It's very tiny at the moment. We're getting a long way away from it, and it's also fading into the twilight in the evening. In both months, it sets before 9, and it's just barely dark at 9. Saturn is excellent right now. You might have seen Mike's pictures from a week ago of Saturn on the transit of Titan. And it was beautifully presented, as long as you're up at 4 o'clock in the morning, it looks lovely. Otherwise, you have to wait till after midnight before it comes up, and about an hour earlier than that, 2 hours earlier than that, when you get into September. Uranus is very well positioned too, but a lot of people don't look for it, but it is underneath the Pleiades star cluster. So it shouldn't be too hard to find a general area of it. It doesn't move very quickly, so it's not very far from the Pleiades in a month from now. Neptune is interesting. It's very close to Saturn, so if you can find Saturn, you can find Neptune probably for at least part of the time in the same field of view in the telescope. And they separate gradually as we see, but they do hang out together so that Saturn will always lead you to the vicinity of Neptune. So we look, here's Mars on this evening, or in a day from now. You can see Mars is right here, very, very low in the sky. In this depiction, the sky is not even dark. So you're looking at 10 degrees above the horizon in the deep twilight. About 9:45 in this case. So it's really not an observable object. If you see it, it's only to be able to see, say I saw Mars. I hope that's not me. When we get into August 19, I sort of just picked a time in the middle of the month. You can see here we are in the morning around 3:45, and Mercury, here's Jupiter and Venus at this time very close together. Mercury down here just above the horizon, but being as far as it is from the sun, which is down in here, then it should stand out fairly well. You'll be able to see it easily in binoculars. Uranus is up in here all by itself, and then Neptune and Saturn are together up in here, just a short distance apart. And I've also marked constellation of Orion. Orion is a sign that winter's coming, but it's also one of the nicest constellations for some observing and photography because of the Orion Nebula that's right here in the sword of Orion, number 42 in the Messier catalog. So this is actually a pretty fine display of planets in the morning, although not all close together. When we go a month from now, Mercury's gone, Venus is now still prominent, but you can see they've separated from Jupiter by quite a large amount because Venus is moving back this way while Jupiter continues on that way. Orion is now quite a bit higher, and if you're up in the morning, it's certainly worth a look with any kind of telescope or binoculars. And we have Saturn in here, and haven't bothered to put in the others. In this particular date, we have a moon in the middle of the sky. So it's kind of a go out and see the planets now if you're going to watch them. So here we have some interesting things going on here. The Milky Way, I've already mentioned that. Saturn and Neptune have a conjunction tonight. Well, it's actually tomorrow night. But they'll be getting closer together for about 3 days before they pull apart. And by conjunction, about a degree apart at their closest. So that getting any kind of a morning clear sky, even just with a pair of binoculars to get up and stand on a balcony in our backyard and take a look at them. It's quite an impressive set because Venus, of course, is the brightest planet and Jupiter is typically the second brightest planet. So we end up with a spectacular little pair of planets together. This happened a year or two back too, and it was in the evening sky and a little easier to see. We have the Perseid meteor shower. I'll have quite a bit to say about that. That begins in a few days and generally peaks on the 11th to the 12th. The meteor shower is a long drawn out one, and you can watch it up to a week on either side of that. We have a little bit of a pairing of these two with Mercury down toward the horizon on the 20th, which would also be a nice picture and a nice way to look at them. We got a quarter moon in the Pleiades, but we've had better mixtures of the Pleiades and a quarter moon in past months. Nevertheless, that's kind of worth a look. But again, you get up in the morning. We're into the zodiacal light when we get into September. I'll talk a little bit about that. And of course, I've already mentioned that Orion is becoming a little more prominent. That's probably our favorite winter target over the time. So here is August 10, 12:39 in the morning, so a little after midnight. That's about then that Saturn and Neptune are at their closest, 1.5 degrees apart. And so you get a binoculars would be overkill for this because they would fill a small part of a binocular field depending on how much magnification you have. If a bit of a telescope that could make an interesting picture, well, you probably want to bracket exposures because Neptune's quite a bit fainter than Saturn, and putting the two of them together would be a little bit of a processing challenge. But if you could do over a 1.5 degree and get enough of a photograph, you could probably throw in a couple of moons of Saturn and even a couple of moons of Neptune in that picture, depending on how you do it. Somebody somewhere in the astronomy community will take that picture with 2 planets and several moons, so it might as well be one of us. And you get the next night, you can see they've pulled themselves apart now. They're 2.16 degrees. Up here we see, that's a month from now. Up here you see how each one of them has moved in a month. Neptune's moved quite a bit less than Saturn, of course, because it's much farther away than Saturn. So they now at 2.16 degrees apart, still pretty decent. So basically you're going to have Saturn and Neptune together in the sky for at least a month and probably a little bit beyond that. Well, this particular night I seem to have a moon in there as well. When we take a look into August 11th and 12th, we have another conjunction, but this one is the one I talked about Jupiter and Venus. Here you see them at their closest, 4:45 a.m. But you know, Venus is very bright and Jupiter is too, and you can probably see them in the daylight when they're well above. You don't have to get up in the middle of the night as long as you can find Venus, which is usually pretty easy with a pair of binoculars or sometimes just by eye. And once you have found it, you'll be able to see it by eye. So you just have to point a telescope at Venus and you'll find Jupiter in there too. So if getting up at 4:45 a.m. isn't your forte, then try it in the daylight. And closest approach is just a hair under 1 degree, so twice the width of the moon. Perseid meteor shower, again, peaks on the 11th of the 12th night. It's one of the more popular meteor showers. It's not the best one, but it's a pretty good one. It's popular because of the season, so you can tend to watch that in fairly warm temperatures. But you're going to want it without a sky full of smoke. And we also have a problem with about being 3 days or 2 days after full moon. So the sky is pretty bright, but you know, the Perseids are good enough and the moon is low that you're going to be looking more toward the northeast and overhead. So you're going to get a pretty good dose of meteors as long as you go out into a dark part of the world and you're happy to spend some time there. In the evening, you tend to get longer trails. Once you get after midnight, the trails tend to be a little shorter. We'll show you that in a minute. Tend not to look directly at the radiant, which is where they seem to be coming from in the sky. I'll show you that in a minute. As you get into the later part of the night, into the morning, it sometimes better to look underneath the radiant where you're seeing meteors going down in the distance. There's a bit of a trade-off there because when you look down low, you've got a lot more atmosphere you're looking through, so you see you have more chance of seeing meteors in it. But of course, the thicker atmosphere takes away from the fainter ones, so it's a bit of a toss-up whether you see it more or less by looking under the radiant. So here's what the meteor shower looks like. Here's the Earth moving along in its orbit, and at the same time it's also turning. And so the meteor shower, the meteors are coming from this direction, and on the evening side, you sort of, because you're moving out of daylight here and rotating into the evening sky, you're getting meteors that graze the atmosphere. And so they have long, long trails, in part because they tend to be higher up in the atmosphere. But as you turn into this, the motion of the Earth plus the rotation of the Earth is actually adding to the speed of the meteors. And so you end up with brighter ones. So it's quite a bit of additional velocity. Whereas if you get, once you get into here with their head on, you're not adding anything from the rotation and not very much from the revolution. So the meteors tend to be shorter here because they penetrate directly into the atmosphere. And so you see shorter trails, but probably brighter ones because you're looking at sort of light that's less attenuated by that distance. So that's why we sort of have a trade-off on, by the time you get into this part of the night, the radiant is higher up, so you get a better view of meteors coming from all directions instead of just rising up across the sky. Personally, I prefer the evening one if the weather's really good. But if it's a really good shower, it's just there for all night long. Now, a bit of a picture here from, you can see how these meteors all appear to be coming from some point in here. These are taken from 32 images with trails. But one of the things about taking pictures of meteors is you need a fairly fast lens and a very, very high ISO. So these are 8-second exposures because I wasn't tracking at all. But the thing is when you trace each one of these streaks back, except for these are sporadic meteors, this one even here. But when you trace all of the meteors that came in the part of the Perseid meteor shower, you see they all come back from this area, which is the radiant. And you can even do this visually by marking meteors on a star chart. And very quickly, you'll be able to identify the area that the radiant is. From night to night, that radiant moves a little bit because we are, after all, in orbit around the sun, and they would appear to be coming from a slightly different point. Here's a somewhat different picture taken from a different year of the Perseids. I wondered about these automatic telescopes, the Dwarf 3 and C-Star, and how well they would do. Well, the Dwarf 3 is an f4.3 system, which is fairly slow, and the C-Star is an f5, which is even slower. They tend to have not a very much of a wide-angle view. But I think it would be worthwhile to try those and take a series of maybe 30-second exposures. You'd have to test it to see how bright your sky background is. And then you can assemble them into the assembly that I've got here. To make this kind of a picture, you actually have to take a background image, maybe with one meteor on it, and then paste each one of them in individually and match them up with a background so that you can.
The Dwarf 3 does have a wide angle view.
Yeah, the wide angle is okay. It's still this f4.3 that might limit you. I'm not sure, it may be more sensitive than a camera, for instance, and it's not as limiting on that. That's what I say. You need to really try it and see how well it works out. But you know, this lens that I have here, you can see there's an enormous amount of area that is in it because it's a 15 millimeter lens. compared to 3 times longer, or 10 times longer here and 15 times.
Things are different, man.
Yeah,
It's
So-
got a separate lens, separate system, and that, and the C-Star 30.
Yes, 30.
you can find pictures of meteors taken with those cameras. I didn't find anybody that had put together an assembly like this. So now's your chance. There's a fair number of C stars and D3s in the crowd, so it's worth the trouble. Interestingly about this, although it doesn't show so much here, these meteors are green at the start and red at the end, and that's because when they first come into the atmosphere, they have very high speed, so they're glowing with a greenish color, which is due to the elements in it that are vaporizing. But as it gets deeper into the atmosphere, it's slowing down, and the temperature of it drops, and so it glows red instead of glowing green. You won't notice that too much by eye unless you get a very bright, long-lasting meteor, but certainly shows up in photography. This is this sort of conjunction. We have a moon here, Venus and Jupiter. This is after they've separated quite a bit. We're into August 20 here, and we still got Mercury down in the corner here. This sort of constitutes a pretty picture because the moon is a very thin crescent at the time, and usually that works quite a bit better when you have 3 planets that are pretty bright. Ordinarily, the moon would swamp, although even a full moon in here would do it, but you won't get a full moon over there at this time. And then with this Pleiades star cluster here with the moon, not very interesting picture unless you just happen to be there. The brightness of the moon will swamp out the star cluster. In the past few months, we've had the moon moving past and into the Pleiades, which was a more interesting view. The zodiacal light. These are photographs here. The zodiacal light is this globe here, and here it is here, and here we have the Milky Way here. So you can see they're sort of a comparable brightness, but quite different appearance. And it's a cone of light. The sun is down here, so this cone of light is sticking up above the sun. And the reason it's there, it's a reflection of sunlight off of dust. And the dust is just an ordinary component of the Milky Way or of the solar system, and it's sort of spread out across the solar system from stuff that's been thrown off by the sun, from meteor dust, that sort of thing, and it just sort of spreads out along the orbit of the sun. So when we get into September, and it'll actually be mid-September and a little later, for about 2 weeks, we're passing through the plane, the sun's orbit, and the dust becomes a lot more visible. It's a little bit like the smoke we have. When the smoke is aloft, you can see through it pretty easily. You know it's up there, the sun has a funny color and everything else. But when the smoke is down on the ground, you begin to see that even a block away, it's beginning to obscure things. It's much, much more visible when you're looking through it horizontally than when you're looking through it vertically. And so normally we're looking through the dust almost through it from the side, but at this time of year, when we're at the equinox, we're looking at it edge on. So here's this is the equator of the Earth, and this is the apparent path of the sun in the sky. So when the two of them are in conjunction, which happens in March and September, that's the time when you're at the right angle with respect to that dust to be able to see it. And so the reason that you see it in the morning has to do with the ecliptic. Now, the ecliptic is the path of the sun in the sky. So here we are in the evening in September, and you can see that the ecliptic is very, very low. But when you get into the morning, the ecliptic is very high, and it forms quite almost a 90-degree angle with the horizon. So the zodiacal light sticks straight up in the morning. And if you were to watch it in the evening, it's very low and hard to see because it hugs the horizon. So at this time of year, we see the zodiacal light in the morning. And then when we get into March, the situation is reversed, where the morning zodiacal or equinox is here, and the evening one is bulging up. And so we tend to favor the morning at this time of year and favor the evening in March. And there we go. Another AI generated image. Show me two cats looking at Saturn. Thank you.
It was excellent, Jay. Thank you very much. And we're now up to the point in our program, I think, where we actually are on break. So this is the opportunity, if you have any interest in exploring, our lunar scopes, or talk to anybody about calendars, or any of the other questions that came up during the announcements. Does anybody have any questions before we go to break? No, so we'll probably take, looks like probably 15, 20 minutes. We can be back and ready to go. Just a brief biographical, I guess, introduction. Put my legs back. Thank you. Dr. Zari is an assistant professor jointly appointed in the departments of physics and electrical and computer engineering at the University of Alberta. She is also Canada CFIR AI Chair and Research Fellow at the Alberta Machine Intelligence Institute. Her research group aims to develop the use of machine intelligence for scientific discovery in space science and exploration. They focus on addressing outstanding challenges and uncertainty, quantification, and the inclusion of physical information. These challenges are broadly shared between scientific domains, and the group's focus centers on probabilistic machine learning and inverse problems. Dr. Azari is also a science team member of the NASA MAVEN mission to Mars, where she leads machine learning research as relevant to studying Mars' space environment. Previously, she was a UBC Data Science Fellow and a postdoctoral researcher at UC Berkeley's Space Science Lab. Her PhD is from the University of Michigan College of Engineering's Climate and Space Department, where she was an NSF Graduate Research Fellow and NASA Earth and Space Sciences Fellow. Dr. Zari spent several years in space and climate policy at IDA's Science and Technology Institute for pursuing graduate education. Please join me in welcoming Dr. Azari to present to us this evening. Thank you, Dr. Azari.
Great. Thanks, everyone. Feel free to tune me up or down as you need to. All right. So it sounds like we are good on the echo. If anything looks awry, just let me know. I think you're probably going to be seeing the presenter view, but I actually don't know. So let me see if I can get going here. All right. So how does this look for everyone? Good, you're not seeing the presenter view, you're seeing the normal, boring, one slide at a time view?
Yes.
Wonderful. All righty. So, hello everyone. As introduced, I'm Abby Azari. I go by Abby, not Abigail, in case you have any questions and want to ask me them. So I wanted to give you a brief tour of the challenges and promise of machine learning for understanding planetary space environments. And just to get started, just kind of to introduce this overall picture of where I see machine learning, is that, in my view, the future of kind of space science and exploration broadly has started to require machine learning to do the types of science that we're interested in doing, to answer the types of questions that we're interested in answering. But as of this moment, out of the box methods, so kind of all of these kind of news items you see about AI, as well as ChatGPT, these methods are insufficient to answer all of our scientific questions in the field. And so kind of as introduced, the research group that I run at the University of Alberta and at AMI, the AI center that I sit at, aims to answer fundamental questions in kind of scientific domains related to space by advancing our ability to use these methods to actually answer the questions that we're interested in. Okay. And my group kind of focuses in 4 main areas. The first is scientifically informed instrument autonomy. So how can you operate scientific instruments in really harsh environments very far away, say at Mars or Uranus, Neptune, etc. The second is including machine learning into large physics-based models, right? So science often uses these very computationally intensive physics-based models. How can we use machine learning to help us there? And then I have an additional 2 items, but today I'm mostly going to talk about what we can do with machine learning to understand space weather at Earth, Mars, and lunar exploration. Okay. So the way in which we kind of as a group focus on answering and addressing those kind of 4 main topics is really diving into 3 main needs that we have in science. When you're doing any type of kind of machine learning or automated analyses. The first is uncertainty quantification. So estimating the uncertainties that you have in a model or in your observations. The second is interpretable methods. So how can you understand what machine learning methods it is that you're using and what the answers might tell you. And then finally, including physical knowledge, right? And so this is kind of my worldview of the space that I exist in. And I just want to start that off with this kind of overview before we get into what we're actually going to talk about today. So today, this is kind of like a 2-part talk. The first part is going to be just general overview of machine learning and planetary science. What is happening? Where is the field going? What I think kind of the highest reward areas are. And then the second item is going to be more of a traditional, I would say, astronomy kind of focus area talk, which is how we're applying machine learning methods to actually understand something about a system, right? And both of these are published papers. So if it's 8 p.m. and you're having trouble staying awake, you can take a note of where these exist and read them perhaps in an earlier time at your own leisure. So this first paper was a white paper. So what this means is it was a community effort from myself and several other what I would consider kind of early career students and postdocs, very early professors who got together and we all said, you know, in planetary science, we're all seeing kind of some issues in the machine learning use that we have. What can we write for the broad field about what's happening here, where the field is going, and where we would like it to go in the future? This was published in 2021, and machine learning moves so fast that that paper is already quite dated. And so now it's actually fun to read it in hindsight to kind of look into the future at the time. And then the second paper is going to talk about what we are doing with machine learning for understanding Mars and Mars's space environment. So as this presentation keeps going, try and kind of write down your questions because you might have some that are going to be more broad about machine learning and some that might be a little bit more specific about Mars for topic number 2. So topic number 1, why do we need machine learning in planetary science? I think this is a good question to ask at this time. I think machine learning is used a lot right now, and it's always good to ask why we actually need to use it. And in planetary science, we have reached a point where just due to the sheer size of data sets that we get back from missions, if you want to use those data sets for statistics or for large scale analyses, you have to be considering automated methods. And if you're considering automated methods, then you are more or less considering machine learning or data science. And the reason for why this is because planetary science has really expanded in the types of data sets that we have now as compared to the past. So I like to date kind of the beginning of our field, the field that I sit in, to the early 1970s, late 1960s, when we first started sending in situ or satellite missions to other planets in our solar system. And these missions collected a data size on the order of about 100 gigabytes. 1 gigabyte, for reference, is about 30 minutes of a video stream, as it's not a lot of data that was coming off of these first kind of planetary missions. Jumping into kind of what I would consider the modern era, we have missions like the Mars Reconnaissance Orbiter, MRO, as well as the MAVEN mission, which I'll talk about more later, which are collecting more data than all past missions combined as a single mission in MRO's case. And in MAVEN's case, MAVEN now has over 20,000 consecutive orbits around the planet. So if you're kind of in the business of trying to understand Mars, which I am, then you're dealing with a problem that you really cannot look through 20,000 orbits by hand without slowly losing your mind, right? And so at that point, you really need to start considering something automated to do the types of science that you're interested in doing. But this is not the same, this is the same story in kind of other fields of space. So if you look at kind of my field of space physics at Earth, there's missions like MMS. MMS is actually a mission of 4 separate spacecraft. So that's 4 spacecraft orbiting Earth. That mission alone is collecting about 13 gigabytes of just science relevant data per day. We have imagers taking constant pictures and videos of the sun, like Solar Dynamics Observatory. That mission is collecting about 1,500 gigabytes of data per day. If then you jump to Earth science, you'll have missions like the Sentinel series, also known as Copernicus. This is collecting 20,000 gigabytes of data per day, right? So this is all kind of pushing us to consider machine learning as necessary in the scientific workflow. And if you remember kind of in your kind of introductory science courses, or just kind of what you think about science, the framework is usually you'll formulate a question or a hypothesis, you'll then investigate that answer, and then you'll interpret the results. Now, how you do that chain kind of depends on both your question, but also the methods that you choose to pursue. You have kind of very classic experimentation and observation, right? So this is like telescopic observations of other planets, of other stars. You can write down some mathematical equations that you think might describe the scenario, theory. And then one of the things that started to emerge in the last, I want to say 10 to 20 years, maybe 30 at this point, is data science, right? So understanding the world through the lens of statistics, machine learning, AI. I would put those all into this general umbrella of data science. And that has really started to be what has come up in the last kind of 30 years of the scientific workflow. Because it is relatively new, scientists, including myself, are still thinking and coming up with new ways of answering questions through this methodological approach, right? But unlike kind of other fields, it's not just about the size of data that we have that's causing us to think about machine learning. Oftentimes, where we might want to send a mission or how we might want to send a mission requires us to use autonomy or some sort of autonomous system to get there, right? And one of the like kind of hallmarks that I point to for missions requiring autonomy is the Dragonfly mission, which is planned for arrival at Titan. Titan is a moon of Saturn, in case you forgot or never learned. And Titan is very cool in terms of science. I think it is going to be a very, very interesting mission that we will be able to gain data from. And this is a dual quadcopter. So it's basically a little flying, not so little, a flying kind of drone-like object, which is going to fly around on the surface to different locations to understand possible life supporting conditions. And if you kind of think about how far Saturn is from Earth. It's quite far. The time it takes to send a message from Earth to Titan is more than an hour. That means if you want to communicate with your cute little flying drone that you've sent to Titan, it's going to take you an hour to send any type of message there at least. And that means that you have to do this autonomously. There is absolutely no kind of human-based control that you'll be able to do real time. You'll have to either send commands and wait or handle some sort of autonomous functioning to deal with this, right? And this has led to kind of a wide range of applications of machine learning and AI in the field at this point due to these needs. How we as a field kind of organize ourselves is pre-mission planning, mission operations, and post-mission analyses, kind of all centered around these workhorses of the field of planetary science, which is the missions that we send. And some of the things that I think kind of most people are familiar with is once you have the data, what are we going to learn from it, right? And so this is kind of that big data world that I was introducing before. But there's increasing interest about how you can prioritize the observations that you see, right? So because you can't send back all the data and because it takes a long time to communicate to whatever it is that you've sent, you might want to prioritize what it is that you would like to send back to Earth. And if you do that, how are you going to do that in an autonomous way? And then there's also kind of judging or estimating what you think you might find when you go somewhere, right? And then you want to evaluate a lot of different scenarios and judge or estimate the risk of different scenarios of where your satellite's going to go, what it's going to measure, etc. Okay. So this has pushed the field of planetary science as well as the field of other kind of scientific domains into really investing and using machine learning in our scientific process. So what is being shown here is a chart of the percentage of papers that discuss machine learning in four different fields that are all represented by NASA. So until recently, I was in the United States, and kind of the point of this chart was to kind of estimate what parts of NASA represented science were doing machine learning at the time. And so you can see purple here is astrophysics and astronomy. Orange is heliophysics, so this includes space physics and space weather. Green is earth science, and then blue is planetary science. And over kind of the last several years and decades, machine learning usage has increased, as kind of surprise to no one, given anyone seen the news. But planetary science has not really kept the pace of these other scientific fields. That is relatively odd, primarily because we have, in a lot of ways, the same types of data, right? So earth science and planetary science, this is the same type of instruments that you might send, you're just sending them to a different place. And so this kind of raised a question in myself and my co-authors' minds about like, why is this happening in planetary science and not other fields? This was something that we had anecdotally noticed as people working in the space, but we wanted to know kind of why are there more people in astronomy and data science and less people in planetary science and data science? Like, what is happening here? And the reason that we largely came up with is that in planetary science, we're often faced with environments in which we have limited observations, right? So if you think back to kind of the examples I was showing you about the time history of data set sizes, if you consider the Voyager missions, which were on the kind of left side of that chart, some of the earliest missions, those are still the only missions that was sent to some planetary bodies in our solar system, including Uranus and Neptune. So if you only have sent one mission, it's very difficult to build a complete model, either physics-based or data science and machine learning based, about what it is you're going to expect about that system. And kind of coupled with that, if you're going to send a future mission again, you still require autonomy to sufficiently explore that space. So we have this kind of dual push and pull where we are challenged to use machine learning because we have limited observations, but we have to because we're going to have some form of autonomy to explore that system, right? And so this, I think, has more or less artificially limited the applications of machine learning in our field. And so as part of the kind of white paper that myself and others put together in 2021, we identified that a useful thing for us to do as a broader community would be to identify kind of data science, machine learning as another core fundamental method branch of science that we want to invest in for the sake of understanding in the field. And one of the things that we kind of were both happy and disappointed to find was a very useful reference from 1979, which is over here. I'm showing you a picture of it, where very similar recommendations were made around that time about the need for autonomy and robotic exploration in planetary science, and the requirement of investment in that. At the time, that was called machine intelligence, which you'll still hear around in the field. It's kind of an older term for AI these days. And this is something that I kind of enjoyed reading. You can find this online if you get a kick out of reading kind of older documents, which I do. You might enjoy reading that one as well, right? But let's say you're a individual planetary science or hobbyist. Kind of the first three things that I would recommend, like what do you do in this space where it's hard to use machine learning? The three things that you can focus on are more or less the same three things that I like to focus on, which is how do you estimate your uncertainties about the system? Because they are going to be uncertain, right? You don't have as much data as other uses of machine learning. We don't have the entire internet to train on. We have one mission that went to one planet in the past. How you can use these methods to actually interpret the answers that you're getting. And then finally, how you can include whatever physical information you prior understand about the system, right? But I always think kind of talking about doing science is cheap until you actually start doing it. So I want to transition at this point to topic number 2. And let me just make sure I actually have some amount of time. I do. Awesome. Which is now that we've seen the space, right? We've seen kind of where machine learning might be useful for understanding planets. How are we actually going to apply this? And this is from a paper that I published last year. This is kind of an interesting paper. I see it as something that is happening more and more in the field, which is the core kind of effort or finding of the paper was not what's in the paper itself, but what it comes with, which is a software kind of package that you can use to predict some physical quantity at Mars, right? And the paper actually describes that software and how to use it, what the limitations are, and how to use it for science. Okay. So the problem that we were attempting to solve through this effort was a rather, I would say, kind of fundamental / simple one, which is that Mars does not have a satellite that sits upstream in the solar wind and constantly measures the solar wind, right? And on later slides, I'm actually going to describe what the solar wind is, what a planetary space environment is. So just kind of hold on for your questions until then. Hopefully I'll describe enough of kind of these terms so that you'll at least understand kind of where I'm coming from. But the fact that we don't actually have a physical asset that's measuring the solar wind at Mars means that it's really difficult to quantify or to understand how the solar wind might be affecting the environment around Mars, just because you don't have a measurement of it at all the time that you might want it, right? And so this has unfortunately, fortunate somewhat for me, because then I could write this paper in this project. But this has somewhat unfortunately impacted our understanding of Mars as a system entirely. This has limited our understanding of atmospheric dynamics, or of ionized atmosphere or ionospheric dynamics. Has limited our understanding of the magnetic field around Mars, of space weather, so how kind of temporally dynamic solar wind events might be affecting Mars, as well as estimating how Mars's aurora might be dependent on the solar wind, which you would assume that it should be. And several other people besides myself have kind of talked about this problem. I really like a paper that was written in Frontiers by a colleague of mine that talks about kind of why having a true physical asset would be a really nice thing for the field to have. And it would also help us here on Earth for understanding our own system. All right. So I feel like this talk also should have some educational material in here. And I want to describe a little bit about what I mean by solar max or solar min, about planetary space environments. So to take kind of a jump left into some more basic definitional slides, let's talk about kind of some of these terms that I'm saying. A lot of these terms are coming out of what I would consider a subset of astronomy, which is space physics, or heliophysics is also what it's known as. In my mind, I like to think of space physics and heliophysics as kind of the study of everything inside our local solar system. So if you can actually send a mission there and measure it in situ, it probably somewhat falls under the umbrella of space physics. If you're looking outside the solar system, then you're more in the realm of astronomy and astrophysics. So that's kind of a nice breakpoint to keep in mind. All right. So when I'm talking about solar min or solar max, what I'm actually talking about is the fact that our sun undergoes a rise and a fall in solar activity approximately every 11 years. Right. So this is a video from the Solar Dynamics Observatory, one of these large big data missions that I was talking about, taken at solar min in 2019 and solar max in 2024. And you can see this is actually very close to now, if you just put that together, and we'll talk about that in just a second. But solar maximum corresponds to when the sun's internal magnetic field switches directions from northward to southward, or from southward to northward. And that magnetic environment of the sun becomes very chaotic when that switch is occurring. And some of that chaotic behavior you can see observationally through sunspots. And this is something that you can actually see from Earth with a very kind of basic telescope setup, is you can track sunspots and count sunspots. And this is something that we've been doing kind of as humans for a very long time. The reason why they look darker is because that they are cooler regions and they have more concentrated magnetic flux. This appears darker because they are cooler as a result. And this can spawn eruptive events. So sunspots are usually the regions where you might get different types of space weather being spawned from, including solar flares and coronal mass ejections. Now, a long-standing way of tracking solar activity is by just counting the number of sunspots. Right? So you can tell kind of the last time I gave this presentation was in the early 2025. So my chart needs to be updated into the first half of 2025 now. But this is that kind of unnormalized sunspot number. How many sunspots do we see in different times, right? And so you can see we're very close to solar max right now. And you can kind of track this back roughly to the late 1700s, possibly further. And we are now within a maximum period, likely for the next year or so as well. And these kind of rare solar wind events affect planetary space environments, including Earth's. You might have noticed we've been getting a lot more aurora lately. These two pictures are actually ones that I took. This is from British Columbia, which you would not expect to see a lot of aurora in. It's always a little bit too cloudy. So we got very lucky during this particular event, which was in May 2024. And in May 2024, we had over 80 very large flares coming from these kind of active regions, which you can see with sunspots usually. And this is a video from Solar Dynamics Observatory from that time, showing that active region kind of erupting with energy and causing, through subsequent effects, the aurora that we were seeing during that month of May in 2024. This is kind of the prettiest aspect of space physics, in my opinion. The less pretty / slightly harmful effect of space physics and space weather is the fact that when Earth's geomagnetic environment is disrupted, which sometimes results in these types of aurora forms that we can see and kind of ooh and ah. This can also disrupt Earth's power grids as well as our satellites, right? And so the field of space weather is kind of interested in a wide range of physics, including the aurora and its formation, as well as a more operational question, which is how can we prepare for Earth's power grid in different locations to prevent any types of power outages or other types of satellite issues that occur during space weather events. Now, when I say space environment, I truly mean the environment around a planet that stretches from kind of its ionosphere, so its ionized upper atmosphere, to the solar wind. Usually it ends in definitional terms at a bow shock, right? So similar to how kind of a boat travels through the ocean, you can consider a planet kind of traveling through the solar wind, through a fluid flow, and at the forefront of that interaction, you'll get a shock structure. So this is where the analogy to a boat comes in, is where you can look kind of on the front part, the bow of the boat, you can look down, you can see the shock being formed in front of you. That is a very similar idea to what is happening here. Okay. And the solar wind, which is coming kind of from our sun at all times, is this supersonic flow of charged particles, or plasma, that we usually describe with a magnetic field as well as a velocity. And those quantities that we're kind of measuring are highly dynamic in time, and how that kind of temporal dynamics greatly affects what you might see downstream. All right. Now, if your planet has a magnetic field, you would usually call a space environment a magnetosphere. And when your planet does not have a magnetic field, usually you would just say it's a space environment, or possibly an induced magnetosphere if you're trying to be a little bit more technical. All right. Now, for studying planetary space environments, we are generally interested in how a temporal change in the solar wind, let's say we have a unique space weather event that's happening, or a kind of more calm, slow change from one solar wind sector to another solar wind sector. How does this kind of temporal difference drive what we would measure downstream, right? So how does that affect our planetary space environment? How does it affect our radiation belts, the aurora, etc.? And the way in which we kind of think about space environments is, in general, is usually along two kind of primary axes. Now, I made this chart in PowerPoint, so don't read too much into it. You already noticed the planets are not to scale, and there's no numbers on this chart. So this is very much a kind of general picture of how you can think of space environments. Usually how we think about space environments is that they can be externally driven. So driven in terms of its mass, momentum, and energy through the system from the solar wind, i.e. the sun is driving kind of that dynamics through the system, or internally driven, where planetary sources are the main kind of mechanism that is moving mass and energy around. And usually kind of a hallmark internally driven system is Jupiter, because this is a very fast rotating planet, because you have moons like Io, which create plasma. Jupiter is a little bit less sensitive to the solar wind dynamics than other planets are. And then the other axes that we usually consider is if you have a magnetic field or you don't as a planet. So to our current understanding, Venus does not have an internally generated magnetic field. Jupiter does have one, and that also changes the dynamics. You can see exoplanets here. I put in this kind of mystery box of we're not quite sure yet. Also, there's a lot of them, so I would expect them to all exist somewhere on this chart. And then Uranus and Neptune are also a little bit of a mystery right now. We know that they have magnetic fields. They're not terribly well characterized, and future exploration is hopefully planned in the next several years. So if you remember, after this tour, we're supposed to be talking about Mars. Why are we talking about Mars in this lens? And the reason why is because Mars is this kind of complicated case where it is considered a hybrid magnetosphere. Or in other words, it has features of both induced or non-magnetized space environments and intrinsic space environments or a magnetosphere, right? And you can see kind of, I put this little cartoon up where on one axis we have a weak or no magnetic field induced. On the other side, we have a strong magnetic field or an intrinsic magnetosphere, and Mars is somewhere in the middle here. The reason why it exists in this middle is because Mars actually does have some magnetization. It is not a lot. These magnetization regions are called crustal fields. This is kind of implying / known to be magnetic fields that are thought to have been resultant from a priorly active global dynamo that became extinct in the history of Mars. And kind of the main interest for Mars scientists about kind of why these crustal fields matter is in how they might play a role in the loss of Mars's atmosphere. So to our best understanding, Mars used to have a very analogous in terms of pressure atmosphere as Earth does now, mostly CO2 in particular in the Mars case. And how these magnetic fields and their kind of prior iteration played a role in the loss of Mars's atmosphere is kind of this ongoing, interesting question that we're trying to investigate, right? And so kind of to pose it a little bit more firmly, the role of magnetization in whether an atmosphere is lost or acceleratedly lost or decelerated, i.e. retained, is kind of this active area of inquiry. Now, dependent on what your solar wind is doing at the same time, you might get a very different answer. So you kind of have these two competing things that you're trying to quantify. One is what your planetary environment is, where the crustal fields are. Some regions on Mars have a much stronger magnetization than others. That's what these colors are showing you. And then temporally, the solar wind is always changing. And so it's very difficult then to break apart the magnetic fields and the solar wind as these two kind of primary mechanisms that you're trying to measure, right? And these spatially varying magnetic fields have impacts in combination with the solar wind at Mars for what you would consider the magnetic fields to look like on a global scale, what the aurora looks like, how you can measure it, etc. If you are interested in Mars's aurora, there's actually been several recent papers. One of the rover teams, the Perseverance rover, actually turned their camera up to take a picture of the aurora on the surface, not just from up down, but from down up. And this, if you can kind of look at this picture enough, is actually confirmation of the aurora. if you compare the left and the right, that is kind of where you look. It's not the most, I would say, enticing, but it is kind of a factual estimate of the aurora occurrence. We also have aurora over Mars that are quite, let's say, less diffuse and more kind of sinuous or discrete. That is what is being shown here. This is from another Mars mission called the Emiratis Mars mission, EMM. They have an aurora camera, which is looking kind of from space at the planet. And what is being shown here is that kind of auroral emission is very different from what you see at Earth. And we're still kind of trying to understand why you get this type of different morphology. And then crustal fields also affect atmospheric and ionospheric dynamics, like I was mentioning before. And so there's been kind of a large amount of attention and interest in that type of study. So how are we currently estimating the solar wind? Right, so I just showed you a bunch of results saying that solar wind mattered. And I was also saying that we can't estimate it very well. So how do those two things go together? How are we currently doing this? And the answer is that we are putting together what limited information we have to create proxies, or to create kind of our best guess of what the solar wind should be when we can't actually measure it directly. Right? And the way that people have been doing that is that they've been combining a bunch of different measurements from a bunch of different missions. At this point, there's a kind of history of Mars's relevant measurements from about 2000. There's been several missions. Here's that MAVEN mission that I was mentioning before. And each one of these missions is measuring a slightly different quantity, maybe at a slightly different energy range. And we're all kind of trying to put together a cohesive picture from all of these missions about what the solar wind should be doing, or what we think it is doing at all times. Right? So one of the kind of primary missions that is measuring the solar wind is MAVEN, as I was mentioning. And the reason why it's particularly useful is it has one of the more complete data sets for this problem. It has plasma as well as neutral instrumentation, so charged and non-charged instruments that you can use to measure different populations. And this is very useful for measuring the atmosphere, ionosphere, solar wind, as well as space environment. Now, the kind of problem with MAVEN is that it is another one of these missions that's an orbiter, which means that as MAVEN orbits, I'm showing you one of these orbits that MAVEN has undergone of the now over 20,000. As MAVEN orbits, it will measure the solar wind, and then it will pass through the shock structure that I was mentioning, and then it no longer measures the solar wind anymore. So as you orbit, you will have wonderful, pristine solar wind measurements, and then you will start measuring what you actually want to see the repercussions of the solar wind upon. And so you always have kind of this structure of here you can measure the cause, here you can measure the effect, but you never measure them at the same time. And that is relatively tricky then to create cohesive understanding, right? So what previous people have done is kind of trying to put together this cohesive picture given these observations. And I am going to go a little bit faster just to make sure that everyone can stay awake until it's not too late. But feel free to ask me at the end if you have any questions. So these prior approaches usually have some kind of limitations to them. Either you will only get one estimate for every 5 hours, or you do not have a full estimate of the uncertainty, right? So I just described a very difficult problem. That problem has an inherent uncertainty to it just because of the time delay between when you're measuring and when you're not measuring. That is just a very difficult problem. It should be highly uncertain. Some of our prior attempts have not been. And so this kind of issue motivated what I have started calling the virtual solar wind monitor at Mars, right? So this is Virtual because we don't actually have a satellite doing this. This is a kind of fitted or estimated quantity. And just to kind of illustrate why this was needed, until this product kind of came online, if you wanted to kind of draw a correlation or estimate a correlation between a solar wind parameter and a downstream measurement, you usually had a data set that looked something like this, where you'd have one solar wind estimate for a bunch of different downstream measurements. This is very hard to kind of claim a lot of like when this goes up, then this goes up type of analysis. If you can break this apart, i.e. have multiple solar wind estimates for these dots, spread them out, then you'll have a much better chance of kind of estimating how this parameter might drive this measurement, right? And so that was kind of the main reason why we went after this. So what is a virtual solar wind monitor for Mars? In short, what this is doing is it provides a continuous estimate. So you can get it kind of at any time, as long as MAVEN was either arrived at Mars and has not been discontinued at Mars. So this provides a continuous estimate of the solar wind with a bunch of different quantities that we use to describe that physical phenomenon. And they each have an uncertainty or a range at which we think is all kind of valid, right? So we'll have a mean estimate and then a standard deviation uncertainty. So how does VSWIM work, right? This is a machine learning talk. VSWIM is a machine learning product. More specifically, VSWIM is using something called probabilistic machine learning. So this is estimating a distribution, not just a single answer. So it's best to think of it as, here is all the different estimates of the solar wind that we think are relatively valid. And here is our general estimate of how wide those uncertainties range. Right? Gaussian processes, this type of machine learning that we're using here, scale to how much data you have. Specifically, their uncertainties scale to how much data you have. Right? So on the left, I'm showing you a case where the dots are in observation. So we have two observations on the left. And then this pink shaded region is what your model would predict. If you have more data, which is what we're showing on the right, so each dot is another data point, and you can see it's been filled in here, then your fitted model has more confidence in the answer, and that shaded region decreases. Right? This is really useful for the type of data set that we have here, because if you have more data, you can be more confident. But if you didn't measure the solar wind for a long amount of time, let's say 5 days, which is a real gap in our data set, then you want to be very uncertain about that. The solar wind is dynamic. If you don't have a measurement, then you should be pretty uncertain about what the solar wind is doing at that time. So this is kind of the non-mathematical explanation of what VSWIM is actually doing. And kind of at its core, VSWIM is solving an interpolation problem. If you have some observation here, you have some observation there, how do you draw a line between them, right? So this is a pretty kind of, I would say, instinctual response to how you would solve this kind of issue in your data set. And you can see here is kind of what I'm showing you as an example of one single orbit of VSWIM's estimate. So these are all kind of different solar wind parameters. And the black dots are true measurements. The colorful kind of bloom-shaped animal-looking envelopes are where you don't have a true measurement. And this is where VSWIM's uncertainty quantification really becomes important, is because it's an estimate of how certain we are about what happens in between these 2 points. Now, this is very useful for kind of the field, because this enables us to use the MAVEN data set at a much better capacity than we have before. So it has a relatively kind of accurate performance as long as you are within 2 days of a true solar wind measurement. That occurs for roughly 2/3 of the entire MAVEN dataset. So this enables, in other words, you can use VSWIM for about 2/3 of the entire dataset's lifetime, and it will work very well. If you expand that to 10 days or 80% of your entirety of the MAVEN dataset, then you'll be able to get a moderately accurate uncertainty quantification. The exact answer is going to vary, so it becomes a little bit less confident, but you're still kind of welcome to use it for downstream scientific tasks. Right. Now, there are some limitations to this. I've been talking quite a lot about like kind of dynamic temporal events. That's very difficult to estimate with a model like this. If you remember my kind of balloon animals, were very smooth. Solar wind is not that smooth. And so some of the kind of future work that I'm kind of pursuing now is how we can include other types of estimates into this pipeline, right? So to kind of skip forward, if you want a more dynamic estimate, you have to include additional information. The two main ways in which you can do that is you can include other missions, or you can include physics-based models. And so this is kind of where VSWIM is going in the future, is to try and capture the more dynamics of the solar wind. So in summary, hopefully that wasn't too nap-inducing at this hour, but this should have given you an overview of machine learning and planetary science, should have given you an idea of what kind of real applications are looking like. And as a bonus / snuck in some slides, you've hopefully learned some fun facts about the solar cycle, about the aurora, and about space physics. So with that, I am happy to take questions. If you don't have any, you're welcome to email me later.
Thank you very much, Dr. Azari. Sure if we have any, yes, we do have a few questions in the audience. If you wouldn't mind helping some of those questions, we appreciate it. Sure.
You got a mic?
I'm not sure if we can plug, can she hear us? Dr. Azari, can you hear us?
I can hear you. The questions might have to be repeated for me, but we can do this.
Provide some data from survey telescopes. And there's always something you didn't think you'd find or didn't know you could find. Is machine learning going to miss some of these things? There aren't enough graduate students in the universe to sort through it all. So will the machine learning programs pick up the stuff that's totally new to us that we need to know?
Dependent on what type of machine learning you are doing, potentially. So if you're just kind of looking for something different, like here's all of our data, and here's something that's unique or new or an outlier, right? Something we've never seen before, that is a very nice and well-posed machine learning task. So potentially, yes, it does somewhat depend on the outlier. Machine learning's discovery of new physics is not terribly well supported yet. It still requires a lot of human effort and human in the loop, right? So as long as you pose it correctly, it's a feasible thing.
We have another question. Judy Anderson, go ahead.
So thanks very much for a really interesting talk. It took quite a neat turn there toward the end. I haven't wrapped my head around those things yet. But I wonder two things. One is, are you able to find any signature of the inhomogeneity of the crustal features on Mars? And the second, sort of related, are you able to use the inhomogeneities in, say, iron deposits on Earth and what we might measure around the Earth orbits to help you figure out how to analyze the data that you are collecting in Mars?
Mm-hmm. Yeah, so this is a nice question. Thank you for asking it. The work I presented here doesn't really have that answer in it. But to address the first half, the inhomogeneity of crustal fields on Mars, you can see that in our data set. It is not in the examples I showed you here. It's in some of my prior work. But you can see very distinct spatial organization of aurora, of ion and neutral particle populations, of magnetization, especially at very close scales to the planet. And then it kind of drops off as you get to higher and higher altitudes. So roughly by 800 kilometers altitude, you see less and less of that very kind of specific scaling of the crustal fields. But above that, there is still some effects, just at a much larger scale. So Mars has stronger crustal fields in the southern hemisphere. And I will kind of make you a little blind right now by flipping back. But if you notice, if you squint really closely, this bow shock boundary is actually further away in the southern hemisphere than the northern hemisphere. And that is a crustal field effect. So that is one of the kind of larger scale effects. There are much more interesting smaller scale effects that you see too. In terms of Earth, yes, there is shared kind of methods that people use coming out of geophysics for estimating these fields, for fitting models to them, physics-based and machine learning-based. And there's also a fair amount of shared kind of geochemistry studies that people are doing in terms of like how these fields are formed, what we think is happening. And so I would say, yes, that is a ripe question. There are crustal fields on our moon. There are also crustal fields on our planet. There's also anomalies in our magnetic field. The South Atlantic anomaly is one of them on Earth that causes some global effects as well. So I would say, yes, there's a lot of kind of lessons to be learned between the planets.
Okay, we have one more question here. In your virtual solar wind model, how many features were there? You flash that
A
equation.
lot. Yeah. So to answer this, there's kind of two different ways of answering this. I'll answer it both ways. You can choose which one makes the most sense to you. So in terms of machine learning, usually you consider features to be the inputs that you give your machine learning model. So to answer it that way, the entire kind of input space is the data that happened after your estimate and the data that happened before your estimate. So it's actually a huge amount of input. But in terms of like the actual physics interpretation, there are 10. There are 10 features that we are actually measuring or estimating, right? So it's the magnetic field is this top row, and that is a vector quantity. So it's X, Y, and Z of the magnetic field and its magnitude. It's a velocity, another vector quantity. So it's X, Y, and Z of the velocity. So how fast the solar wind is moving, the temperature of the solar wind, and the density. So you can choose which one. I'm going to take a guess and think that you meant the second answer, but feel free to correct me.
All questions. So which machine learning model works best then?
Which one works best?
Yes.
Yes. Oh, echoey. So if you want to use a machine learning model on this problem, and you care about uncertainty quantification, I would say the machine learning model that I chose to use, which is Gaussian processes, works really well here. There is a cost to Gaussian processes on this data set, and that cost is time. It is a very slow model. The trade-off is you get uncertainties, but at computational cost. other models do run faster. I would argue that they do not give you a full picture of what the possible solutions could be. So it really depends a little bit on what you're interested in. If you care about uncertainties, this model works well. If you care about a singular answer that might possibly be wrong, but runs very fast, then there's other models that work. And kind of the classic workhorse for that is neural networks, which are kind of the majority of machine learning today.
And one more question. Are you employing methods to generate synthetic data in with training models?
In this example, no. In other work I'm doing, yes. So for some of the work I do, I am kind of running physics-based models and kind of fortuitously iterating between a physics-based model, machine learning-based model, a physics-based model, machine learning-based model. And through each one of those kind of loops, I will generate a synthetic data set to then compare to observations. So dependent on kind of what it is that I'm doing, yes, for this, I wouldn't really call this synthetic data. It's not truly like of the same quality, right? So like you can just kind of look at it. This is super jaggedy and variable. And then as soon as you're within the model prediction, it's very smooth. So I wouldn't call this necessarily synthetic data. It's a little bit too focused on smooth and uncertainty quantification in this case. Yeah.
I guess I just have a quick question myself, and that's just with the solar wind, I guess there's the solar max and solar min. Are there fluctuations, or do you have to do all your analysis and during the solar max in order to gather the data you need? Does it happen during both min and max? Are you gathering the same level of data, the same quality of data?
Yeah, no, that's a great question. So I'm using this to shamelessly show this video again because I really like it. But the short answer is there is this 11-year periodicity to the solar wind, right? You have more variability every 11 years. The orbital cadence of MAVEN is so short that recovering this periodicity is difficult. So with our model, we don't truly have an issue in terms of the sampling of our training data set for solar min or solar max, simply because we have so much near-term temporal like data that recovering this 11-year cycle is not necessarily a huge concern in our data set. So like MAVEN started in 2014 here and has now gone here. We don't quite have the time history to actually recover a full solar cycle at large confidence. Instead, like we're dealing with sub-second and sub-minute resolution. So year time cycle is not necessarily within a feasible periodicity to recover yet. Yeah.
Okay, thank you. Any other questions? Oh, one more. Go ahead.
Are you able to use your virtual solar wind to refine measurement of the loss of atmosphere in Mars?
That is the hope. Yes, that's why I made it. That is effectively the end goal here is now that you have a data set that you can get every minute of MAVEN's operational lifetime estimated and have an uncertainty on it, then you can actually do some very interesting statistics and you can actually do some correlations with magnetic fields, with crustal magnetic fields. You can compare it to Earth because we have that type of data at Earth, much better even than what this is. And so I think yes, that's where we're going. I don't have the answer yet. But stay tuned.
Thank you. That was an excellent presentation, and thank you for spending time with us, Dr. Azari. And the level of questions we had, I think your presentation was well received and very exciting for us. Thank you.
Yeah, great. Cool. Hope to see some of you in person someday.
Okay, well, I guess that, I'll put the more volumes on here. Everybody, that wraps up our center meeting for this month. Please rejoin us again in September. It's on the 12th, I believe, if I have the date correct, Friday the 12th. That'll be our next center meeting, and stay tuned for the topic and the announcement for the meeting to come out probably in about 2 weeks' time. Thank you, and see everybody at Boston Pizza. Don't forget that's on tonight. I'm sorry. Oh, Spruce Woods, that's correct. Spruce Woods, don't forget that we have the Spruce Woods Star Party, August 22nd to 24th. Spruce Woods, Manitoba, very close to Brandon. So, and please make sure that you get the Eventbrite's
On the website.
or on the Eventbrite link and register as soon as you can. Thanks very much. Again, $40 for individuals, and children under 12 are free. Thank you again, and have a good evening, and we'll see everybody next month. If I don't see you at Boston Pizza. Thank you.
Good job.
Hey, how are you?